Today we'll discuss about combinational circuits. Here you can see total 126 slides. Okay, it means I listed all the topics of combinational circuits. I will discuss important points on each topic. Then if you have any doubts, I will clarify. Okay, so this is like a revision and doubts clarification session. First, everyone should know about definition of this combinational circuit. Output depends on present input. Only I will discuss only important things, not everything. Okay. And you have to know the steps necessary to design any combinational circuit: symbol, truth table, simplification of each output, and from the simplified equations you have to draw diagram. That will become combinational circuit. Okay. Now coming to multiplexer, we call it as a universal circuit. But if you take a demultiplexer, it is not universal. Okay. Universal means you can implement any circuit by using multiplexer. Any circuit means it can be combinational, it can be sequential, any. Okay. I told you I will discuss only important things. Okay. If someone asks you, you can say multiplexer is a data selector. Generally you do always 2 by 1, 4 by 1 like that, but here you can see 3 by 1, 5 by 1 also I did. And this is the most important question: how to implement logic gates by using mux. Yeah, Shravan, any doubt?
Sir, actually, multiplexer will take 2 power n inputs, right? How to implement 3:1 and 5:1? Could you please?
Okay, okay. Suppose here the meaning of 3 by 1 is, suppose when we say 2 by 1, it indicates there are 2 data inputs. When we say 4 by 1, 4 data inputs. But data inputs always may not be 2, 4 even numbers. There can be 3, there can be any number. Suppose now if I take 3, it will become 2 power n. Okay, here you can see the relation. Here 2 power n is the number of data inputs. N select inputs, 1 data output. In this case 3 equal to 2 power n. Now if I want to send 3 data inputs to output, how many select inputs I need? So here our intention is you need to send A to output, you need to send B to output, you need to send C to output. This is the target. Suppose if I take one select, I will get 2 possibilities. With 2 possibilities I can send either A, B or C, any 2 only. I cannot send 3. So to send ultimately A, B and C, you need to take at least 2 select inputs. So for 3 by 1 also you need 2 select inputs. But when you take 2 select inputs, 0, 0, 0, 1, 1, 0, 1, 1. Just out of 4, 3 combinations are enough. With 0, 0 you may send A, with 0, 1 you may send B, with 1, 0 you can send C, 1, 1 you can send again another. Same one input is repeating. Okay, now. But here to send ABC, this 3 combinations enough. Still any doubt am I in this?
Got it, sir.
Okay,
Thank you.
okay, good. After explaining important points on all topics, once I will show you all each and every slide. If any doubt in each and every slide, I will explain, no problem. Okay, so until this we finished implementation of logic gates. Now on multiplexer you will get some problems like you need to implement any circuit, any boolean equation, even in gate exam also. Okay, so they will give some SOP, POS with don't care, without don't care. Okay, so here what are the points you need to remember, I will tell. For example, this is a 3 variable expression. They asking with 8 by 1. So you can directly take 8 by 1. These 3 variables you can connect as select inputs. If it is SOP, this given values you can connect to 1. Absent values, it means with 3 variable 2 cube, 8. 8 means 0 to 7. Out of 0 to 7, whatever absent here, they can connect to 0. Like that you can directly do. But if this same variable 3 variable expression, if they given, if they ask you to implement with 4 by 1, then how to do? But before going to that, suppose here, okay, yeah, this is clear, this is clear. Suppose here, if there is a don't care, that don't care also you connect to 1. Remember, 3 variable expression 8 by 1. This all present, if it is SOP, all present 1. Even don't care also to 1. Absent values to 0. Okay, clear. Now this 3 variable expression, if they ask with 4 by 1, how to do? Now we need implementation table. For example, here I did, see, same expression 3 variable 4 by 1. You need to take only 4 by 1, but you need to implement this whole expression. Now we got implementation table. So here the question is, previously 3 variables you taken because 8 by 1 as selects, but now for 4 by 1 you should take only 2 selects. You cannot take all. If I want to take 2 selects, which inputs I can take as selects? That is the question. Suppose here I taken BC. You may think, sir, why taken only BC? There is no rule you should take only BC. You can take any 2 variables as inputs, select inputs. But what is the logic behind that? Okay, I will tell you the logic. First, what you need to do, you need to draw the truth table like this. 3 variables they given. Na? With 3 variables, generally how many possibilities you will get? 8. And these are in binary. Here I written decimal. Now here 0 0 0 means 0. So in the equation 0 is there? No. Here see. No means output is 0. 1 is there? Yes. Output is 1. Like that you can write all output values. Okay. Now start doing implementation table. Suppose for example here I taken BC. With BC I will tell so that later you can understand, you can take anything. Suppose when I take BC, whatever remaining I will take in the implementation table. So that A will get 2 possibilities, A bar and A. Now this A all zeros indicate this A bar, this A all ones indicate this A. Suppose when A bar nothing but 0 and BC are 0 0, what you selecting? Suppose here if you write 0 0 0 1 1 0 1 1, suppose if I write 0 0, this will be selected, this will go to output. Okay. Now here how to write these values? Suppose 0 means A bar and here 0 means A bar and this BC 0 0 you can assume, so that you will get whole combination. Now what is the decimal value for this whole combination? 0. So now that decimal combination now you writing here. Like that for 0 0 1 what is the decimal combination? 1 you writing here. 0 1 0 decimal combination 2 you writing here. After writing like this, whatever the values they given here, those values you need to round. Here you rounded. Suppose if you take column wise D naught, 0 and 4 nothing rounded, so output 0 if nothing rounded. If both rounded, output 1. If any one rounded, this slide 6 means A will come. Here 3, A bar will come. Okay. So like this, when you take BC as select, A will come here. You need to take numbers like this. Suppose now I will do in another way. I won't take BC, I will take some other. Then approach. The approach means here the numbering order will change. And remember, when you taking 0, wherever you started 0, there you need to write D0. Suppose you can start 0 here, 1 here, 2 here, 3 here. In that case, D0 will be here. Now this D0 equal to 0. Now this is D0, that will be 0. Like that. Now same problem I will do with some other. So here it is BC, same previous only I taken. If I take some other thing, I will show. Because this problem is important, that's why I am explaining. Okay, now let us take AB as select. Now if I take AB as select, now implementation table, in that case C bar C will come here. Now if you draw the table, okay, already table is there, we'll look into that and we'll do. Now if I draw C bar here, what it means, this 0. Okay, where zeros are there? Here decimal value 0, and where next 0 is there? Here. It means here 0 will come, then 2 will come. Because this complete row is belongs to A bar. Now in this case complete row belongs to C bar. Suppose complete row belongs to A bar means you need to write 0, 1, 2, 3 in the row wise. Now complete row belongs to A, you need to write 4, 5, 6, 7 directly. Now you need to look when you take C, here, 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 here. It means here means you need to write 0, 2, 4, 6. Now you need to write here 0, 2, 4, 6. Again we'll check 0. Because C bar where came? Here 0. 0 how we telling? Decimal 0. This 0 means decimal 2. 4, 6. Now it will become 1. Where are ones are there? Here 1, 3, 5, 7. 1, 3, 5, 7. If you know this logic, you can do any problem. Wherever 0 started, that will be D0. This will be D1. This will be D2. This will be D3. Now, what are the values they given in the equation? 1, 3, 5, 6. Now go and round those values. Why you rounding those values? If this is SOP, given values you have to round. If that is POS, absent values you have to round. Remember, 1, 3, 5, 6. 1, 3, 5, 6. Now in this column wise, 6 is C bar. In this column wise C. In this column wise C. In this column wise C. So C, 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 C bar. This is the output now. Now you can take AC as now you can take AC as select. Now you can take B. In that case, what is the numbering here? 0, 1, 4, 5. Here 0, 1. Here 4, 5. Then 2, 3, 6, 7. Here 2, 3, 6, 7. Now whatever the given values you round and you will get here values, you can connect. So there is no rule you should connect only BC. You can connect any two selects, any two inputs as selects. Okay. So this record I will send you. If you did not understand, again you can watch. So print screen, just a minute. Now we implemented one equation. Equation implementing nothing but implementing a circuit. Implementation of circuit. So with this logic you can implement any circuit by using mux. If A, B, R selects. Okay. Now we taken 3 variable and we did with 4 by 1. Sometimes here you can see suppose 4 variable, if they ask with 16 by 1, you no need implementation table, directly you can do. Suppose if they ask 4 by 4 variable expression with 8 by 1, you can take implementation table and you can do. But this 4 variable expression they asking with 4 by 1. Now in this case you will get 2 4 by 1s. Remember, previously you got 1 only. Now you will get 2 4 by 1s. When you got 2 4 by 1s, those outputs you need to do OR operation, and here you need to connect one inverter. This circle indicate inverter. So this change you need to observe. This is again a new problem. Previous problem you can do if the number of variables are n and the size of multiplexer they asked is n minus 1, then only that method is possible. But now this method, number of variables n and the size of multiplexer is n minus 2. Now you need to apply this process. n equal to 4, not n minus 1. Suppose if you take n, yeah, previously how can we say the relation? Suppose this is the 3 variable n, let us assume n equal to 3. What is the multiplexer they asking? N plus 1 multiplexer. Okay, like that we can say the relation. Now n equal to 4. Okay, now you can say 4 variable n equal to 4 expression, the multiplexer also n. In that case this is the logic. You will get 2 multiplexers, and when you get 2 multiplexer, here you can connect 2 by 1, but you cannot connect 2 by 1 because they asked 4 by 1. That's why you need to connect only OR gate. Now if it is 4 by 1, you can connect only 2 selects. Now here out of 4 you can connect only 2 selects, and one variable you can use in the implementation. And what about other variable? That will act as a enable. So this is the concept. Just I am telling the logic because this is the revision session. According to that logic you can go through, and if you did not understand you can ask me, or this lecture already uploaded in YouTube, you can ask me that. Okay
sir, in the enable pin 0 and 1 kuda teeskocha sir adi.
Yeah. Suppose here suppose if I want to send this D0 to D3, this multiplexer should enable. In that case enable value should be 1. So when enable equal to 1, you can send D0 to D3. That time this multiplexer will be disabled. When you want to send D4 to D7, you need to apply enable 0. So 0 become bar, it will work, it will become disabled. Okay, Nama? It will become 0 and 1 both. Then only complete operation will happen. One time it is 0, one time means when you want to send these values. Another time when you want to send these values, it will become, when you want to send this one, it will become 1. When you want to send this one values, it will become 0. Okay, Namma? Clear, Nagadora?
Yes, sir. Yes, sir.
Yeah. Now, 4 variable expression, but they asking with 2 by 1. See, this is the logic. I am giving the logic. In that case, you will take only 2 by 1. So, one select you can connect. Enable also will act as a select, and 2 variables you need to take here. Okay, this is the logic. Now you can say n equal to 4 and the size of multiplexer is n minus 2. Okay. So this is about multiplexer. So in whole multiplexer, what are the important things? Implementation of logic gates and problems. Those are most important for interview. Now coming to demultiplexer, what is most important I will tell. Suppose here also implementation of some equations or implementation of some full adder. Okay, simple. If this is SOP expression, demultiplexer output already, suppose if you see demultiplexer, what gates it contain? AND gates, no? So now if you want to get SOP expression, already product terms coming, just you connect to OR gate, you will get this equation. Simple logic. Okay, so this is one problem with respect to demux. For this full adder, whatever the inputs, those will become select inputs. Now coming to encoder. Suppose if you want to know the definition, mux is data selector, demux is data distributor. Now coming to encoder. What is encoder? Definition. Suppose generally encoding means converting anything to binary. Okay, that is correct. Decoding means binary to any. Okay, but I will give you some more good technical definition. If you see here, for particular activated input, you will get equivalent binary output. Of course, encoder converting this form of data into binary only, correct only. Instead of saying like that, for particular activated input, it will produce corresponding binary. For particular activated input, it will produce corresponding binary. That is the functionality of encoder. Okay. Then what is the functionality of priority encoder? In this encoder, if you observe this row, only one of the inputs should be activated, then only it can encode. Suppose if multiple inputs are activated at a time, it cannot encode. That is the drawback in normal encoder. To avoid the drawback, priority encoder implemented. Priority encoder, even multiple number of inputs are activated at a time, it can encode based on the priority. That we'll see. Suppose same above 4 by 2 encoder, now 4 by 2 priority encoder. If you take a 4, 2 power 4, 16 possibilities will come. Suppose first possibility. In this first possibility, this may become 1, this may become activate, this may become activate, any 1 become activate, any 2, any 3, any 4. Any 4 nothing but all. Any 1 can activate at a time. Suppose in this case only 1 is activated, so D not related output will come. Suppose now in this case X means it can be 1, it can be 0, let us assume 1. In that case this and this both activated. At a time multiple inputs activated. Now if it is a normal encoder it cannot encode, but now it is a priority encoder, it can encode. How? Out of these two, which is the highest decimal value? 1. So D1 related output will come. So out of those two, it is giving priority to the highest value. That's why it is priority encoder. For example, let us take this. If these 3 X's are 1s, all are 1s, all activated at a time, normal encoder cannot encode, cannot produce output, but this is the priority. It will give the priority to the highest value. D3 related output will come. Simple. Okay. Here you can see why this many ones came. with this 4 you will get so many possibilities. Now if you include all possibilities, then this K-map will come. Then if you simplify, you will get this circuit. Okay. Just the difference between priority and normal encoder. When multiple inputs activated at a time, priority encoder can encode based on the priority, but normal encoder cannot do. Okay. The definition same for encoder and priority. For the particular activated input, it will produce corresponding binary output. That's it. Now coming to decoder. Simple. For particular binary input, it will activate corresponding output. How I am saying? For particular binary input 0 0, it is activating corresponding output. 0 0 means it is activating Y0. 1 0 means it is activating 1 0 means 2 na, it is activating Y2. This is the definition. But in the decoder there is no priority decoder. But in the decoder there is another concept. Based on these outputs, active high output, active low output. For example, if there are no bubbles here in the outputs, this is active high output decoder. If there are bubbles, suppose see here, this will be active low output decoder. Suppose here you can see for particular binary input, particular output will be activated. Now here activated is 1, deactivated are 0. In active high, activated will become 1. Suppose if it is active low, activated will become 0, inactivated will become 1. That's the difference between active high output decoder and active low output decoder. Okay, now here for 0 0, Y0 activated. Now 0 means activated because this is active low. These all are inactivated. Okay. And when you telling this input output relation, make sure, for example, if I say this is 3 by 8, n equal to 3, I can say 2 cube outputs matching. Suppose you take 16 by 4, 4 by 16. Now this is 4, this is 16, n 2 power n matching. But that 4 by 16 some people also call 4 by 10. In that case it is not matching n 2 power n relation. So that's why you can say inputs are n, outputs are m. This m less than or equal to 2 power n. Less than or equal to. When you say equal to, it is matching to 16. When you say less than, it is matching to 10. So that's why n inputs, m outputs. M less than or equal to 2 power n. When you saying for decoder. When you saying for encoder, m inputs, n outputs. This m same less than or equal to 2 power n. And for this decoder, mux also you can use with enable or without enable. Sometimes enable is optional. For example, without enable also you can do, but sometimes enable is must. Where enable is must, suppose I am implementing a 4 by 1 with a 2 by 1s. That time enable is compulsory, not optional. Okay. Suppose I am implementing direct 4 by 1. Enable is optional, even you can use, don't use, nothing will happen. Okay. Ultimately, what is the purpose of that enable? To make circuit work or not to work. Working means to make enable the circuit, not working means to disable the circuit. That is the purpose. For example, previously I told when I want to send ABCD, upper multiplexer should work. It is enabling that, below 1 no, it is disabling. That is the purpose of enable. Okay. Now this question will come. How to convert demux into decoder or vice versa. Suppose now this is demux. For example, I taken 1 by 4. How to convert into decoder? Just assume these select inputs as data inputs. Now this select as data. This data as enable. Now 1 by 4 became 2 by 4 decoder. See? Outputs remain as outputs only. Vice versa, you can convert this also. Suppose now these data inputs you assume as select. This enable you assume as data inputs. It will become 2 by 4 will become 1 by 4 demux. Okay. And again in the decoder there is another concept, BCD to 7 segment display decoder. Here there is a common anode type and common cathode type. For example, in common anode type, suppose if I want to get 0, only G segment should not glow, all segments should glow. In that case, if I am using common cathode, whatever should not glow, that should be 1. Common anode, if I am using common anode, whatever should not glow segment, that should be 1. Whatever should glow, those should be 0. If I am using common anode, these all will become 1, this will become 0. That is the logic, simple. Okay. By following this logic, you can design this. Now, the most important thing in decoder, problems. With the decoder, problems will come. They will give you SOP, POS expressions. They will ask with active high output decoder or active low output decoder. Simple. I will tell you this is a shortcut. For example, here this is SOP and they are asking with active high output. Now what is my logic? SOP with active high, what gate you should connect at output? OR gate. See, simple, here you connect OR gate. These all values you list here. With 3 variables you will get to 0 to 7, whatever the values they given, you connect to OR gate, you will get output. That's it. Very simple. For example, if this is POS with active high, what gate should connect? POS with active high, you connect a NOR gate. You just make it NOR. It will become correct. So remember this logic. So why you changing the gate? Because equation changed. According to the equation, according to the active high, active low, to get correct output, you need to change. So this is the shortcut you can remember, so that you can do any decoder problems. So far we discussed mux, demux, encoder, decoder, priority encoder. Out of all these 5 topics, mux is first important, then decoder important. In the mux, problems and the logic gates implementation important. In the decoder, these problems important. And the next, priority encoder, normal encoder difference important. Okay. Next, coming to adders. We will discuss adders at the end because this is very lengthy topic. Remaining topics will finish. Remaining topics means we'll go to multiplier, then we'll come back to adder and subtractors. Now, with respect to multiplier, right, you know multiplier means it will do multiplication, multiplier different, multiplexer different. Okay, multiplier is arithmetic circuit, multiplexer is not arithmetic, it is a data selector. Okay, so here you can see 2 by 2 multiplier, 2-bit multiplier. But when I say this one, I cannot say 4-bit or 3-bit, it is only 4 by 3. So if the both numbers are same, you can say just 2-bit. 3 by 3 means 3-bit. But when numbers are different, you cannot say 3-bit or 4-bit. You need to tell the size only. This is the size. It means the first number contain 4-bit, second number contain 3-bit. First number means I want to multiply 5 and 6. For example, 5 if you represent in binary, it may take 4-bit. 3 if you represent in 6 if you represent in binary, it may take 3-bit, like that, based on the number. Okay, that is the meaning of 4 and 3. Now here in this multiplexer, first how to design is important, but it is important in descriptive or university exam. But what is most important in competitive exams, when you design any multiplier, how many AND gates it will take, how many adders it will take, and what is the size of the adder. This logic I will tell with a shortcut. Simple. If you remember this slide, you can do easily. Suppose 2 numbers may be same. Let us assume first number n, second number m. Sometimes 2 numbers can be different, na? Suppose it is 2 by 2, it is 4 by 3. Number of AND gates, if you want number of AND gates, just multiply n into m, either here or here. Suppose for 2 by 2, how many AND gates? 2 into 2, 4. For 4 by 3, 4 into 3, 12. Number of AND gates, you can easily say, na? And after getting product, in the product how many bits will come? Total number of bits in the product. Just n plus m, here also n plus m. For 2 by 2 multiplier, 2 plus 2, 4 bits will come in the product. For 4 by 3 multiplier, 4 plus 3, 7 bits will come in the product. Final product, not partial product. Now, number of adders. Here, either n or m, because both are same, na? For 2 by 2 multiplier, how many adders will come? 2 adders. But here, for 4 by 3 multiplier, how many adders will come? They taking second number, m minus 1. It means 3 minus 1. 2 adders will come. Here also 2 adders. Here also 2 adders. But the size is different. This is 4 by 3. This is 2 by 2. Now, what is the size of the adder? Is it 1 bit, 2 bit, 4 bit, 5 bit? What is the size of the adder? Suppose if you say 2 bit means it is a half adder. 3 bit means full adder. If you say 4 bit, it is a ripple carry adder. Of course, in the ripple carry adder also, there is a 3 bit ripple carry adder. What is the difference between 3 bit ripple carry adder and full adder? Yes, there is a difference. In the 3 bit ripple carry adder, A0 to A3, A2 will be there. B0 to B3 will be there. To add A0, B0, you need one now. With carry, you need one full adder. That's the difference. There is a difference between 3 bit ripple carry adder and full adder. In the 3 bit ripple carry adder, A0 to A2, B0 to B2. That A0 and B0 with carry in, when you want to add those 3 bits, you need one full adder. It means to construct a 3 bit ripple carry adder, you need 3 full adders. Okay. Now here, what is the size of the adder? Here they are taking the first number to tell the size. Here also they are taking first number. It means here 2, here 4. It means if you go and check 2 by 2, it is a 2 bit adder. Whatever the adders, how many 2 adders, those are 2 bit adders. Go and check. 2 adders, both are half adders, 2 bit adders. Again, when you say 2 bit adder, 2 bit ripple carry adder is different. 2 bit adder, half adder is different. What is the difference between half adder and 2 bit ripple carry adder? In 2 bit ripple carry adder, A0 to A1. When you want to add A0, B0, but including carry in, you need full adder. Okay, there is a difference between half adder and 2 bit ripple carry adder. Suppose now here also they told 2 adders, but what is the size of the adder? Here you can see the size of the adder n. N means first number. 4 bit adders. 2 4 bit adder. This is 4 bit ripple carry adder. This is another 4 bit ripple carry adder. And I told you total number of AND gates are 12. 4, 4, 4, 12. And the number of bits in the product are 4 plus 3, 7. 1, 2, 3, 4, 5, 6, 7. Everything becoming correct. So, this is important for interviews, competitive exams. Now we'll go to comparator. Suppose if someone asks you what multiplier will do, it will multiply numbers, arithmetic circuit. Now coming to comparator, when you give two numbers, it will compare which one is greater, which one is lesser, whether both are equal. Like that it will compare and produce 3 kinds of output. That is made by comparator. Okay. So with respect to comparator, you can do 1 bit, 2 bit, 3 bit and so on. Any bit you can do. What is most important with respect to comparator? For example, here you can see when you looking into 2 bit comparator, you are getting 4 inputs. See, it means 2 bit means A0 A1, B0 B1. This A0 B0 become 1 bit, A1 B1 become another bit. Okay. For 2 bit you are getting 4 inputs. Observe, not 2 inputs. And when you writing these values, how you should write? For example, A0 A1, this value take decimal, and for B0 this value take decimal separately. Don't read this is 2 power 0, 2 power 1, 2 square, 2 cube. It will become wrong. It is 2 power 0, 2 power 1 with respect to A. With respect to B, again it is 2 power 0, 2 power 1. Now you can compare, you will get correct output. Okay, this is one point you need to remember, otherwise you may do mistake. And this position also important. This is 2 power 0. Always you need to write a naught to right side, 2 power zeros. Not only here, everywhere. Okay. Now with respect to this comparator, what questions will come in the interview? They will ask you how many total input combinations, how many will be equal, how many will be unequal, how many lesser, how many greater, like that they will ask. Now, if you know these formulas, you can answer. For example, total input combination 2 power 2n. 2n, this 2n just let us assume 2-bit multiplier, a 2-bit comparator. N equal to 2, 2 into 2, 4, 2 power 4 how much? 16. See, for 2-bit comparator, 16 possibilities will come. Here I kept and so on. Like that 2 power 2n will give the total number of combinations. Now how many equal combinations in this 2 power n? 2 power n means here n equal to 2, 2 square 4. Out of 16, 4 are equal combinations. Then how many unequal combinations? 12 are unequal. Out of 12, 6 are greater, 6 are lesser. Then how to know that? Suppose this is total, this is equal. If you subtract equal from the total, you will get unequal. Right? See here, we subtracted. This is total, this is equal. When we subtract, you will get unequal. What unequal means? Together both greater and lesser. Unequal means together both greater and lesser. If you want to know greater alone, lesser alone, just to do divided by 2 this formula. Now same formula I did divided by 2. Here greater or lesser, here greater and lesser. Greater and lesser nothing but unequal. Okay. This is important with respect to comparator. Now coming to code converter.
సార్ అప్లికేషన్స్ ఏమైనా అడిగితే సార్ మక్స్ డిమక్స్ ఎన్కోడర్ డికోడర్ ఇవన్నీ సెపరేట్గా ఎక్స్ప్లెయిన్ చేయమంటారా?
Yeah, sometimes they will ask, suppose multiplexer. These all circuits are digital circuits we use in digital systems. That is common example. If they particularly ask, for example, mux in communication, demux also in communication. For example, I told priority encoder, Casio, digital piano is there, na? When you press 2 buttons, inside there is a priority encoder. Based on the button decimal value, it will produce only one button output, because inside there is a priority encoder. So like that, some practical examples, applications they may ask. Okay. Right. Now coming to code converter. Code converter, just it will take one code into convert into another code. Now in this case, you will confuse between encoder, decoder and code converter. For example, you take encoder, what it is doing, it is converting any form into binary. That is also code conversion only, na? For example, octal to binary, code converter, right? That encoder, decoder both acting like code converters. In that case, is there any difference between encoder, decoder and code converter? Yes. For example, if you take this code converter, if you take an encoder, it always produce output binary only. But if you take code converter, the output can be any. This is the difference. Again I am telling, if you take encoder, the output is always binary. But if you take code converter, the output can be any, including binary. It can be any. And when you compare with the decoder output always binary. Input, the decoder input. Previously encoder output. Now decoder input always binary. But when you take code converter input, it can be any, including binary. So that is the difference. Okay. So like this you can take binary to gray, gray to binary, BC to XS3, anything you can do. This is normal topic only. But here remember, when you doing this conversion, BCD also 4-bit, XS3 also 4-bit. Of course there is 5-bit BCD also, but now we are doing 4-bit BCD. When you doing this with 4 bit you will get 2 power 4 16, but out of 16 0 to 9 only you can represent in BCD. From 10 onwards you can represent in 8 bit BCD, but you cannot represent in 4 bit. That's why 10 to 15 we show like invalid. Even in XS3 also 13 to 18 we show like invalid. 13 means it is in XS3, its actual value is 10 only. So that's why when you're doing K-map also, you need to consider this don't cares. Then only you will get correct output. If you miss this don't cares, you will get wrong output. This is one important thing you need to remember when you're dealing with BCD and XS3. Okay. Not only here, everywhere. When you're doing K-map with that BCD and XS3. Okay. Now, two more topics remain: adders and subtractors. So far, what we discussed: muxo, demuxo, encoder, priority encoder, decoder, multiplier, comparator, code converter. Out of these 8 topics, what is the most important? Multiplexer. Multiplexer, problems and logic gates implementation. Then what is most important? Decoder problems. Then what is most important? Priority encoder, encoder difference important. Then what is important? Multiplier formulas and comparator formulas. Remaining are normal only. Okay. Now coming to adders and subtractors. In adders and subtractor, what is important? Carry look ahead adder is most important. Ripple carry adder also most widely used adder, that is also important. Adder subtractor also very important, because in every arithmetic circuit always we store negative numbers in 2's complement, and whatever the circuit doing arithmetic operation in our any arithmetic logic unit, that is 2's complement adder subtractor, that is adder only, so it can do addition, and that adder same adder can do subtraction also because of 2's complement. That's why definitely you need to learn about that adder subtractor, especially when you're dealing with processor related projects. Suppose here carry skip, carry bypass, carry save, BCD, XSC adders are there. Those 5 are optional. If you want, you can learn, or you can leave it. Okay. So generally those are important when you go to some high-end projects or some MTech level, PhD level, then only. At BTech level no need, and when you go to project, that time you can refer that. Okay. Suppose if madam not covered those, don't worry. Okay. These are optional. Now we'll start discussing adders. It will finish in 15 minutes. Okay. Generally when you're doing arithmetic operations, you adding suppose complements, 6 minus 5, 5 minus 6 you might done already, or plus 3 plus of plus 5, plus 3 plus of minus 5, minus 3 plus of minus 5, like that you might done different problems, no? You did on paper, but in reality circuit will do that. Now I will explain that circuit. Those numbers I will apply to the circuit. It means I will explain with real-time examples. Okay. Now adder. Generally adder means it will take 2 inputs and it will produce 2 outputs. 2 inputs means 2 numbers it is adding. Now you may get doubts, sir, if I want to add 3 numbers, how to do? Okay. If there is a adder which can add 3 numbers at a time, you can prefer that adder. Or you can add 2 numbers, that result you can add with third number. That is another approach. Okay. So is there any adder which can add 3 bits, 3 numbers at a time, not 3 bits, 3 numbers at a time? Yes, there is a carry save adder. I will show you. Carry save adder can add 3 numbers at a time. I did not observe any other adder which can add 3 numbers at a time. That is the speciality of carry save adder. But what is the meaning of carry save? That I will tell when I go to that. Just I will show you what is carry save. See here, this is carry save adder. Number 2, number 3, number 4. How many total numbers? 3 numbers. At a time it is adding. Okay, that is the speciality. And generally, whatever adders we using in reality, those can be serial adders or those can be parallel adders. These serial and parallel adders are n-bit adders. It means it can add any number of bits. You take two numbers, that numbers you will represent in binary. Based on the number, you may represent in sufficient bits. So, the serial and parallel adders are n-bit adders. To construct these serial and parallel n-bit adders, we use half adder and full adder. And again, half adder we don't use practically, only full adder. The reason is, if you want to do addition of any two numbers, for example, see here, if I want to add say 8 and 7, this is A0, this is B0. When you add these two, carry will produce to the next. When carry came, automatically this column will become 3-bit. So that's why in reality when you want to add any two numbers, definitely you need to add 3 bits, including carry. To add 3 bits you need full adder. So if you using half adder, you cannot add third bit, na? That's why half adder is not practically used. Full adder only used. And by using this full adder, we construct this n-bit serial and parallel adders. Okay. And what is the meaning of full addition, half addition? The actual addition, when you're doing in reality any addition, 3 bits will come including carry, na? That is actual addition is full addition. If you full addition means 3-bit addition. If you are adding less than 3 bits, nothing but 2 bits, we consider that as half addition. That is the meaning of half adder and full adder. Okay. And one more speciality, generally if you take any full adder, there can be 3 inputs and 2 outputs, you will observe everywhere. But in carry skip adder, we use full adders only. If you observe here, sum output, carry output, and one more output you are taking, carry propagate output. If you include that also, how many outputs coming? 3 outputs. So this is one speciality in this carry skip or bypass adder. Along with sum carry, there can be another output, carry propagate. But generally, sum and carry only 2 outputs only. But this is one special condition according to this requirement. That also you need to observe. Okay. Now we'll come from starting half adder onwards. Definitely adders topic important when you're dealing with any processor related project. Or multiplier block. Okay. Ultimately, in a multiplier we do partial products, we do addition, no? That time adders only will do that. Okay. Right here, first you can take half adder. In this half adder table, you will feel different. 1 plus 1 is carry 1 sum 0. How it is coming? For example, logically if you add normal 1 plus 1, how much? 2. If you convert in 2-bit binary, how it will become 1 0. Now this 0, 1 0, no? Always this side will be carry. So that you writing in the carry position, 0 in this position. That is the logic, like that you can remember. Or you can remember it is like a rule. 1 plus 1 carry 1 sum 0 as a rule. In the standard book also it is mentioned as binary arithmetic addition rules. Okay. Okay, these equations you can remember, these gates you can remember. Full addition. When you're doing full addition, you will confuse. You no need to by heart this, you need to know the logic. For example, I will show you. For example, I want to add 1 1 0. First two numbers you add 1 1. Then no, sum 0 carry 1. Suppose 3 ones I am adding. 2 ones completed 1 0. Now third one I am adding. That third one you add here. Now carry sum 1 carry 1. This is the carry this side, you write here, you write here, this is the sum, you write here. So like that you need to know the logic how to add. So don't by heart these values. Okay. When you add two numbers, carry 1 sum 0. When you add three ones, carry 1 sum 1. When you add two ones, carry 1 sum 0. When you add three ones, both will be 1. Just remember that logic. And see, this carry output I can write in different ways. This is one form, this is another form. This is with simplification. Without simplification you will get another kind of expression. So remember, this is also correct for carry out of full adder. This bit I observed in competitive exam. Suppose now here this is the full adder logic diagram. You can do, this is also full adder logic diagram. This is also full adder logic diagram. See, different ways you can do. But this is full adder by using half adders. But this is not full adder by using half adders. But now, what is the difference between this and this? This is block level, this is gate level. But both are full adder by using half adders. Okay. Two half adders and one OR gate you need to construct a full adder by using half adders. And to construct half adder, one XOR and one AND gate. Now, what are different types of adders? I told serial adders, parallel adders. In the parallel adder, there is a ripple carry, carry look ahead, carry skip or save, carry bypass, then carry save, carry select, and there is adder subtractor. This is also parallel adder only. There is a BCD adder, this is also parallel. There is XS3, this is also parallel. Okay, this many adders are there. We will see one by one. First we will go to serial adder. Serial adder, remember, important, generally we call adders are combination circuit, but serial adder is not a combinational, it is a sequential circuit. Remaining all adders which don't contain any memory element, those are combinational circuits. Because this serial adder contain D flip-flop, edge triggered D flip-flop, that's why it is a sequential circuit. Now we will see about that serial adder. Now here, to construct any bit, suppose the serial adder can be 4 bit, 5 bit, any bit, you just need one full adder and one D flip-flop. Of course, to store these inputs and outputs you need register, that is common. Okay. But if you take a ripple carry adder or parallel adder, for 4 bit you need 4 full adders. But here, even for 4 bit also, one full adder only. So the advantage of serial adder is simplicity, low cost, low complexity. But there is a drawback. What is the drawback? The addition is slower compared to the parallel adder. That is the drawback. Okay. But you no need to take as a drawback. If you don't want to invest more money, you will go for serial adder. You want it event, so that is speed is not a drawback. Okay. Suppose now, here what we need to know. What is meant by serial adder here? What is the name of serial? These inputs will go one by one. A0, B0 will go at one time. Then A1, B1 will go at another time. So the inputs going one by one. That's why serial. Okay, so the addition also happening, bits also going one by one serially, addition also happening one by one. Okay. Now, that is one thing. Another thing, why we need D flip-flop here? Not some other thing. So, D flip-flop we call delay element. Here, the purpose of D flip-flop is for delay. What is meant by delay? Suppose this D flip-flop giving output after giving input after some delay. Is that correct? No. In that case, every flip-flop will contain some propagation delay. Even SR flip-flop also, after giving input, it will take some delay to produce output. That is not true. So then what is meant by D flip-flop or delay flip-flop? It will produce output after some delay, but that output exactly same as input. That is meant by delay flip-flop. Same data you are getting after some delay. Delay or data flip-flop. So any flip-flop can do that operation, same input output with a delay? No, only D flip-flop can do. And that requirement we need here. That's why we established we are using D flip-flop here. How it is useful here? For example, initially A0, B0 will go. Initially there is no carry, so we assume 0 carry in. 3 bits added, so some 0 will come and carry will come here. Now when this A1, B1 should come, just a minute. So when this A1, B1 should come to the full adder, whenever this carry came and this carry available here. So this D flip-flop will tell to A1, B1, still my carry not came, this carry not came here, you wait. After coming, I will tell you, you come. Like that, how that synchronization happening, whatever clock you connected to D, same clock connected to C here. So this D flip-flop necessary to produce same input output and with a delay and for synchronization also. These all things can do only D flip-flop. No other element can do. Suppose sometimes we convert to some other flip-flop into D. In that case, if you convert T into D, it will be D only. It is not T. Okay, right. So that is the purpose of D flip-flop. Suppose here one question I observed, can I use buffer? If you use buffer, you will get same input output, but buffer cannot contain clock, so it cannot produce synchronization. So we cannot use buffer. Okay, right. Now we understood serial adder means inputs going to the full adder one by one, and addition also happening one by one. That is meant by serial addition. Then what is meant by parallel addition? Is it mean addition happening parallelly? So someone can tell what is meant by parallel addition? Addition happening parallelly? Is it? Are you getting my audio?
Yes, I get it.
Yes, sir.
Okay. So we think addition happening parallelly, but actually addition not happening parallelly. Then why it is called parallel adder if addition not happening parallelly? Based on how inputs going to the adder. So the inputs A0, B0, A1, B1, A2, B2, A3 all will go at a time. So they going at a time parallelly. That's why parallel adder. But addition will happen one by one. How one by one I will show. So serial adder, parallel adder named based on how inputs going, not how addition is happening. I will show. Now this is 4-bit triple carry adder. Let us take here A0, B0, A1, B1, A2, B2 all they will go at a time. But here this full adder 2 can do addition only when this carry available, right? So it will wait until getting this carry. So first it will do addition, then it will do, then it will do, then it will do. So carry is propagating, that is called rippling, ripple carry, propagation delay for carry. That is the drawback here. So it need to wait until getting this carry. Okay. So here this full adder will contain some delay, this full adder will contain some delay, this full adder will contain some delay, this will contain some other delay. Different full adders will maintain different delays, propagation delay. Suppose it will finish in 0.5 second, then it will finish in 1, then it will finish in 1.5, it will finish in 2. Now for this and this 0.5 difference. So now in 0.5 seconds it will finish. Still it need 0.5 second to finish. Meanwhile that carry will come. Still it need 0.5 second. Meanwhile it will come. Like that. So based on this ripple carry adder, you will get some problems in gate exam. something like that. What is the final addition time of this adder? Or they will ask how, when you will get carry, when you will get sum. What is based on individual propagation delays, based on the whole propagation delays also, you will get some problems. Okay, but that is for GATE exam. For your DV exam, just you need to know the concept. That is more than enough. Even if you see the concept, see how many topics are there. Okay, if you are good in concept, that's okay. Even you do spend much time on more example, I think that is no use for a DV exam. Okay, but for GATE exam, you need to practice so many examples. Now here you can see A0, B0, initially we assuming as C in as 0. This is not the first carry, this is the first carry. Okay, first full adder carry, this one, this is the carry in of first full adder, this is the carry out of first full adder and carry in of second full adder. The same acting as output of full adder 1 and input of full adder 2. Okay. Sometimes one question I observed, to construct a 4-bit triple carry adder, how many full adders, how many half adders, like that one question. You need 4 full adders or you need 3 full adders and 1 half adder. Suppose if you don't assume first carry in as 0, you no need this one. Then to add A0, B0, you just need 1 half adder. But now when you add, you will get carry. From here you need full adders. In that case, this is half, these 3 are full. But if you taking initial input carry in 0, you need 4 full adders. So like that you can do. Okay, observe this one. Whatever last carry you will neglect because it cannot be stored. The neglect meaning is there is no storage space because it can store only 4 bit. Whether it is 1 or 0, no matter, there is no space, it will be neglected. That is the meaning of neglect. Now here you can see this 3 bits adding by full adder. So that's why for this one full adder, for this one, for this one, for this one. That's why a 4-bit triple carry adder need 4 full adders. Complexity. The drawback is complexity. For 8-bit, 8 full adders. But if you take serial adder, for even 8-bit also, 1 full adder, 1 D flip-flop enough. So you can do addition, like you can apply some inputs and you can check the output. Okay. Suppose if there is no carry in here, you can make it like a half adder. Then it will work. Okay. Now coming to adder subtractor. Suppose generally adder will do addition, but with the adder only, by applying 2's complement logic, we can do subtraction also. That's why it is called adder subtractor. And that's why in every arithmetic logic unit, the circuit performing addition and subtraction is adder only. And that also 2's complement adder subtractor. What is the logic I will tell. For example, there are 2 numbers, A and B. Generally if you do subtraction, A minus B, you will show like that. But you take A and you do addition only, but don't directly do addition for B. For that B value you take 2's complement. A value as it is, B value you take 2's complement. Now A plus 2's complement of B, addition only will happen because that is adder, but whatever result coming, that will be equal to A minus B. So this is the logic behind subtraction by using adders. Okay, I will show this. How to construct this circuit? Simple. Whatever A value you directly connect to adder, whatever B value don't connect, you connect to the XOR gate. You take 2 input XOR gate. Even it is a 4-bit, even it is a 8-bit, you always need 2 input XOR gate only. Okay. If it is 8-bit, 8 to 2 input XOR gates and 8 full adders will come. Okay. Suppose here, can we take half adder? No. In ripple carry adder, here you can take full adder or half adder, but here full adder compulsory. Okay. Then you connecting A value directly this one, B value to the XOR gate. If you connect B value directly, A value to this, it will become wrong. Remember. Okay. And Another input of XOR gate you connect to sub input or control input or mode input. Then this full adder one in this output of XOR gate you connect here, and A value connected here, and again this mode input you connect here. That is the logic here. Okay. Now when this mode input is 0, the circuit will do addition. Operation is addition, result also addition. But when this mode is 1, operation is addition, the result is subtraction. Okay. For example, here mode 0, I am doing addition only. There is nothing to know. But one point here, when you doing addition, whatever B value you are giving, same will come at the XOR output. You know B value, you can directly blindly write to this XOR output. You no need to check second input of XOR when you're doing addition. But when you're doing subtraction, see here 1. This sub input is 1, and when you're doing subtraction, this output of XOR gate will be inverse to the B value. Suppose this is 0 is the output of XOR gate, and this 1 is the B value, it is inverse. Inverse means 1's complement. It means A value as it is you are giving, A is as it is. B value here you doing 1's complement, and to those all 1's complement value you are adding 1. 1's complement plus 1 will become 2's complement. So A plus 2's complement of B happening. Finally you will get result addition only, but the result is subtraction. That is the logic. Okay. Now when you doing this subtraction, you may do small from large, large from small. Suppose when you doing 8 minus 4, you will get to normally only, you know. But when you doing 4 minus 8, you should be careful. What you need to do when you doing 8 minus 4, you will get not 8 minus 4, 4 minus 8, you will get negative result. When you get negative result, to know the actual result, you need to again do 2's complement. So when you doing large from small, you will get negative answer. So whatever the answer you got here, you will get answer na. For example, somewhere I did, I will show. Finally you will get answer na. That answer, to know correct answer, for that answer you need to apply 2's complement. Then you will get correct result. But when you doing 8 minus 4, whatever the result coming, that is correct answer only. No negative answer na. But when you doing 4 minus 8 like that, to know the correct answer, whatever you got as sum, for that you need to apply 2's complement. Then you will get correct answer. Okay. Now, however, there is a ripple carry adder, there is a ripple borrow subtractor also. However, there is a ripple carry adder, there is a ripple borrow subtractor. It means to implement a ripple carry adder, you take an all full adders. To implement ripple borrow subtractors, I will take all full subtractors. There also sub input, this third input carry in 0, here borrow in 0. The operation is subtraction and the result also subtraction here. Now I will show you another logic. This subtraction I will do with adders. You may think, sir, we already did subtraction with adders, but that circuit will do both addition and subtraction. But now whatever circuit I am showing, this is only full adders. There is no sub input, there is no XOR gate. It will do only addition, but the result is subtraction. When I compare this circuit with adder subtractor can do addition and subtraction both, same circuit in different times. But this circuit will produce only subtraction result. It cannot produce addition result. The operation is addition only, but the result will be subtraction here. What is the logic? It means when I want to do subtraction, I will take full adders only. This borrow in I will connect to 1, and for this B values I will connect inverter. So B values inverting and adding 1, so A plus 2's complement of B happening. So that you will get subtraction result. Okay, right. Now, so far whatever we added or subtracted, those are unsigned numbers. Suppose when I say 8 minus 4, that minus is operation, that is not for number. So 8 and 4 both are unsigned numbers, there is no sign. Now, how you deal with signed numbers? Suppose there can be two positive or one positive, one negative. It can be 4 plus 4 minus 2, or it can be minus 4 plus 2, or there can be two negative numbers. There can be two negative numbers, minus 2, minus 2, like this. Four kinds of problems. Generally you are doing on the paper, but these operations will do by circuit. Who will do? Adder subtractor. Why adder subtractor only doing? Because in every arithmetic circuit we keep always to deal with signed numbers, we use only adder subtractor. Now, first problem. Two positive numbers. Complements are not for positive numbers. Of course, complements are for signed numbers, that also for negative signed numbers. Complements are not for positive signed numbers. These two are signed numbers and they are positive. So you no need to do any logic. Simple, however, in the school days you added, like that only you add. You don't apply any complement to the positive numbers. Okay. First problem completed. Now second problem. It means plus 3 you will convert into sign magnitude, plus 4 you will convert into sign magnitude. This will be A, this will be B. That time your sub input will be 0, because now you want to do addition. Plus na sub input 0. For these four problems your sub input always 0, because you doing always addition. This middle indicating addition, these are indicating signs for the numbers. Okay. Now second problem. Now this plus 4 you will convert into sign magnitude, directly you will apply to A. But this minus 2 don't convert into sign magnitude, don't apply directly with sign magnitude. This minus 2 first on the paper you have to do 2's complement, that to 2's complement you have to apply to B. Okay. Plus 4 you directly apply, but minus 2 on the paper first you do 2's complement, then the 2's complement you apply to B. So A plus B happening, A plus 2's complement of B happening. Your sub input 0 only. A plus 2's complement of B you doing, so you will get to answer. And when you get answer again, suppose in this case positive answer only you will come, plus 2. So that answer is correct only, because positive answer. Now we'll go to another category. Now in this case you will get minus 2 answer. This plus 2 you will directly give to A. This minus 4 first you do 2's complement, then you will give. Then A plus 2's complement of B happening. But the result is negative. When you got negative result, it will be in 2's complement by default. To know the exact result, after getting result, that sum you need to convert into 2's complement, then you will get correct answer. Okay now. Next coming to two negative numbers. Here for both numbers on the paper first you do 2's complement, then you apply. Then you will get negative answer, again you apply 2's complement. Then you will get correct answer. And these four operations will do by adder subtractor only, and that time the sub input mod input is 0 only, because we are doing addition only. Okay. So far we discussed about half adder, full adder, ripple carry adder, serial adder, and adder subtractor, ripple borrow subtractor, and subtraction with adders. Okay. But so far whatever discussed, serial adder drawback is it is not speeder, and ripple carry adder drawback is more complex. And one more drawback, second full adder has to wait for the first full adder carry out to do the addition. So there is a carry propagation delay in ripple carry adder. That is the drawback. Suppose this is a digital circuit ripple carry adder, that carry output may be 0 or 1, because ultimately digital means 0 or 1. If you are able to know whether it is a 0 or 1, you no need to wait for that carry. If you don't wait, you can speed up the operation more faster. If you don't wait means, if you know that value, what is the carry out, is it 0 or 1? Knowing that is nothing but you are looking, you are knowing, look ahead. Carry look ahead, knowing the carry ahead without waiting. That logic is called carry look ahead. So in the carry look ahead adder you no need to wait, so that the speed of carry look ahead adder is faster than ripple carry adder. That's why this is the fastest adder, or carry look ahead adder. But there is a drawback in carry look ahead adder. It is more complex than ripple carry adder. Okay. Suppose if you don't worry about cost complexity, then it is not a drawback. If you're looking into speed, if you're ready to invest more money, more complexity. Okay, right. So what is that logic? How you able to know carry without waiting, without knowing? Okay. Suppose for that you take a full adder truth table. When A B equal to, when A and B both are equal, 0 0 or 1 1 here, what you getting? The C in value not coming. But A and B both are not equal, whatever C in, that only coming to C out. The C in only going here, it means this is propagating here. This is called carry propagate. When A not equal to B, carry propagate. But when A equal to B, this carry in is not going, it means propagation is not happening. It is getting some other new value, it is generating some other new value. So when A equal to B, it is called carry generate. When A not equal to B, it is called carry propagate. So by using this carry propagate, carry generate logic, you able to know what is the carry value, carry out value. For example, in this case, how can you say? For example, we'll go and check. How can we know in the from the ripple carry adder? I will tell you. How can you know carry without waiting for that? Suppose here, let us take this one. When both are 0, when both are 0, this carry out, right? When A and B both are 0 or both are one same, this carry out you are getting some new value. Suppose when both are equal, what you getting? The C in only coming here. When both are not equal, whatever this, you already know this one, this only coming here. So this full adder, no need to wait for this one. You already know this one, this same value you can write here. So this delay you can avoid. So when both are not equal, you able to know. But when both are unequal, how to know? How to know? We'll go to the table. When both are unequal, this is not coming here, some other new value coming here. That is called carry generate. How can you know? I will tell. From the table only, that's it. See, when both are not equal, if it is 0, if it is 1, so here two possibilities coming, 0 1. If it is 1 or 0, it is 0 1. So from this, you know this AB values na, because you only applying. So from these values you can get. And one more thing, but here 0 1 0 1, two possibilities coming. So this is not a best example. I will show you another example. From this equation you can get. So carry propagate, carry generate. See here, this carry generate nothing but AI and BI. A and B values you only applying. If you multiply both, you will get carry generate value. So like this also you can know. This circuit you already know now. What is this circuit? This is full adder by using half adders. Okay. So for dealing with carry look ahead adder, first this table to know carry propagate and carry generate, and then you need to get the equation to implement the circuit. How can you get the equation? From this circuit. This circuit you already know. From this circuit what you need to assume? ABC. Let us assume this is the carry in, this will become carry out, right? If this is the carry input, this will be the carry output. If this is I plus 1. If this is the present carry, this will be the next carry. That's why If it is I, it will be I plus 1. If it is t, it will be t plus 1. So like that you write, and you make everything as in terms of I, ai, bi. This will become pi. So this XOR output indicating carry propagate. This AND gate output indicating carry generate. Now you need to determine this output. Now here pi, ci coming, both product, and here gi coming. Now what is the final equation? You need to write this equation. Ci plus 1 equal to pi ci plus gi, because ultimately OR operation happening. Now however we do serial adder, ripple carry adder subtractor like 4-bit, 2-bit, 8-bit like that, here also in carry locate adder there is a 4-bit, there is 8-bit, and so on. 4-bit adder is called 1 stage or 1 level. 8-bit ripple carry adder is called 2 stage or 2 level. Suppose if you want to implement 8-bit ripple carry adder, you need to implement 2 4-bit ripple carry adders and you need to cascade. That's why 2 stage, 2 level, that is the meaning. So 4-bit ripple carry look ahead adder will be equal to 1 stage or 1 level carry look ahead adder. 8-bit carry look ahead adder will be equal to 2 stage or 2 level ripple carry adder. Okay, now let us see how to design a 4-bit carry look ahead adder. You got this equation, na? If this I equal to 0, how this equation will become? If this I equal to 0, it will become C0 plus 1. C0 plus 1 means C1. This will become Z0, P0, G0. This equation is the first equation. Like that later you substitute I equal to 1, then I equal to 2, then I equal to 3. 4-bit means I equal to 0 to 3. For I equal to 0 to 3, you will get equations C1 to C4. I equal to 0 to 3 only, but C values 1 to 4. Like that C1, and you will get C2, and you will get C3 and C4. 4 equations will come. Now take those 4 equations, implement the circuit. Now this is called 4-bit carry look ahead adder. How to implement? I will show you one equation. For example, let us take C1. What they connected? P0, G0, one AND gate, and P0, C0, one AND gate with the G0 OR operation. P0, C0 AND gate with the G0 OR operation. That is giving C1. Then what is meant by P0? Propagate A0, B0. What is meant by G0? AND operation A0, B0. Now when you doing C2, the C1 is coming to C2. You can see C2 equation. When you're doing C2 above, C2 here, see C1 is coming. So that the C1 you can feedback here. P1 and C1 is there in C2 now, that's why. Like that you connect. Now this is called 4-bit carry look ahead adder. This circuit only some people ultimately this all digital circuit will be in the IC form. For this this is gate level, you can show IC level diagram also to this. Okay, now we'll compare serial adder, ripple carry adder, carry look ahead adder and adder subtractor. For example, for n bit here need only one full adder, one D flip flop, but here n full adders. Here we always tell in terms of AND gates and OR gates, that's why I am not telling here in terms of full adders. If you take this one, n full adders and n 2 input XOR gates. If you take speed, it is slower, it is faster than serial, it is faster than serial and ripple carry. If you take this one, it is faster than serial but slower than ripple carry adder and carry look ahead adder. This one, this one. Now if you take complexity, it is very less complex, it is more complex than serial, it is more complex than serial and ripple carry and even adder subtractor. And if you take this one, it is complex than serial and ripple carry adder but less complex than carry look ahead adder. Okay, it do only addition, it do only addition, it can do, it do only addition, but it can do addition and also subtraction. Okay. Now coming to carry skip or bypass adder, what is the logic I will tell. Skip or bypass means, suppose this is initial carry in. Initial carry in, you sending here and you sending here. Bypass road, generally we call bypass road. Suppose when there is a bypass road, it may go to the village or it may go directly bypass also. So whatever carry it is going and you bypassing also. Based on that, the name came carry skip or bypass. You are skipping, you are bypassing carry. Okay. But what is the logic in this? How it is doing addition, I will show you. Let us take this example. 7 plus 8, I converted into 4-bit. This is 0 triple 1 for A values I applied. 1 triple 0 for B values I applied. Initially carry in 0. Now carry C0, A0, B0 when I add, you getting sum and carry. You writing here. And for this A0, B0, if you do XOR operation, it will give propagate. Like that, you getting for propagate for all full adders, and this will be the final carry. Now this final carry, whatever coming, it is going, and this all propagates going to XOR. If all propagates are 1, XOR output will become 1, so select will become 1. Okay, and the same carry coming here. And inside whatever 1 0 there in multiplexer, those are fixed. So now according to this select input is 1, so this 0 will be selected, it will come out. Now this will become the final carry of this addition. Now this is the final carry of the addition, and whatever S0, S1, S2, S3 came, that will be the final sum. But ultimately sum you are getting here only, but to know the final carry you need to do this two also. So to construct a 4-bit or n-bit carry skip adder, you need n full adders, 1 n input AND gate, and 1 2x1 multiplexer. Okay, like this it is doing addition. Now coming to carry save adder. Carry save means here it is adding 3 numbers at a time. Generally A0, B0, C0. Now the C0 is not carry, this is the third input. When you add A0, B0, C0, and there will be suppose when you add these 3, you will get carry, right? But here we are not taking carries. We are not taking means you are saving the carry. You are not considering means you are saving the carry. That is the meaning carry save adder. Then how it will produce output? This A values, B values, and third input C values you are applying here. Then it is doing addition, sum and carry coming here. This carry you sending like X0, and this sum you sending like Y0. Same happening here. And the last Y3 you fixedly connecting to ground. Okay. Now this sum you directly taking in the final sum. And when you adding these two, whatever coming sum you are taking here. Sum you are taking here. Okay. Here also these two sum you taking here. These two sum only you taking here. These two sum only you taking here. And final carry, this ripple carry adder final carry you taking here. Okay. This will become the final carry here when you adding these 3 numbers. And this will become the final sum. Now see this final sum 9 only. Of course 1 0 extra came, but this answer is correct. Okay. So like this it is doing addition. Here to construct carry save adder, you need n full adders and 1 n-bit ripple carry adder. Okay. Now coming to carry select adder. Here carry select means, I will tell what is the meaning of select here. Now here I am taking 2 numbers. When you dealing with carry select adder, first on the paper only you need to add and you need to check the result. First on the paper. Okay, that is the process. Then after doing this one, this A values you applying here, B values you applying here, or here X values, Y values. Okay, X0, Y0, and initial carry in is 0. And same again X0, Y0, again you applying here, again same X0, Y0, whatever you applied here, here also you will apply. But here one time you assume carry in as 0, here one time you assume carry in as 1. Fix. Okay, right. Now here carry out, this is the sum, and when you add these two, this is the sum and this is the carry out, you forwarding. Okay, finally this value come here, this value come here, these all values coming here. Okay, now first I told you will do on the paper na. When you're doing on the paper, initially you will assume carry, right? Now here when you got 15, when you assume carry in as 0, so here the actual result 15 you got when you assume carry 0. That's why you select when you getting correct output when you assume carry 0. That's why you select carry 0 as select of this mux. Suppose if you getting correct output here when select input is 1, means you will assume this select 1, this carry 1 as select of this. So that's why this is meant by carry select. You are choosing this carry or this carry as select. Now we chosen this one based on, because whenever this carry in is 0, that time we got correct output. Okay, now this select will be 0, means all selects, this select also will be 0. Now here inside this 0, 1 are fixed, I written, but those are fixed. Okay, now if this carry is 0, this 1 will come here, this 1 will come here, this one will come. If this carry is 0, this 0 will come here. Now this 0 is the final 0, final carry, and these ones are the final sum. Like that it is doing addition. So this is meant by carry selected. Now coming to BCD adder. Simple. With BCD adder you need to know 3 problems. Here to construct in this carry select adder, to construct n bit carry select adder, you need 2n full adders and n plus 1 2 by 1 muxes. That is the count. Now coming to BCD adder. Suppose now here BCD means I am adding 2 plus 3. In each number only single decimal digit. Suppose if I am adding 12 plus 13, how many digits? 2 digits in each decimal number. Then that is called 2 digit BCD. Now here only 1 digit, in A and B only 1 digit, decimal digit, that's why it is called 1 digit BCD adder, or if you convert this each digit into 4-bit binary, because BCD means 4-bit, you can call it as a 4-bit BCD adder. You can call 4-bit BCD adder or 1 digit BCD adder. To construct 4-bit or 1 digit,
సార్ అక్కడ 3 మనం యాడ్ చేసుకోవాలి సార్. ఇది యాక్సెస్ 3 అంటే మనకి వేరేది ఉంటుంది కదా సార్, యాక్సెస్ 3 అనేది.
access 3, okay, I will come Amma. Yeah, next to that only I will tell. Now this is BCD. Okay, BCD okay, you are thinking this 3 I am adding. No, this is one number, this is another number. Suppose number A 2, number B 3. Okay, na? Right. Yeah, I will tell. Okay, good observation. So now to construct 1 digit or 4-bit BCD adder, we take 2 4-bit triple carry adders, or we can say for n bit BCD adder 2 n bit triple carry adders we need to take, and 2 AND gates and 1 OR gate we need to take. Okay, now suppose some people this gates they will replace by NAND gates, that also okay. Now how it is doing addition I will tell. Suppose when you are adding 2 numbers, if this result here first triple carry result greater than 9 means automatically this carry will become 1, so that it will become 6, so that for this invalid BCD 6 is adding, so here you will get valid. Suppose if this result is less than 9 but this carry out is 1 means, then automatically it will become 1. That time also invalid BCD, so 6 will be added. That is second case. Now coming to third case. If this result is less than 9 or equal to 9 but carry out is 0, then it will become 0 only. So for now this is valid. For the same 0 adding means same result will come. So like that, when this result is greater than 9 or less than 9 with carry 1, 6 will be added. If this is less than 9 or equal to 9 with carry 0, then 0 will be added. It is nothing but 6 is not adding. Like that addition will happen. Now coming to XS3. Here also this is 1 digit or 4 bit XS3 adder. How it will do addition I will tell. I am taking two numbers A equal to 2, B equal to 3. What should be my result? 5. Now here in XS3 you always need to apply inputs as XS3. Suppose 2 means you add 3 here, 5, you apply 5 here. You show like a 2 but actually it is 5 because it is in XS3. It is 3, you add 3, it is 6. You have to show 3 only but actually it is 6 in XS3. Before only you need to apply in XS3. Now then here sum will come. Then what will happen na? If this carry is 1, you need to add 3. If this carry is 0, you need to subtract 3 from this result. Okay, for example in this case carry is 0. Then I need to subtract 3. But here I established, if you want to subtract here you can use ripple borrow subtractor. But here I am using adder only. In that case, how can I subtract? You can apply 2's complement logic. Na? This number as it is, this result what you do, whatever this result you getting, you do 2's complement to that. You do 2's complement to that. For example, 0 is coming. Na? 0 coming means it will become 1. Now it is 1, it is 1. That same 0 coming here, fixedly here it is 1. Now 1 1 0 1. Now this 1 1 0 1 nothing but 2's complement of this value. It means this is as it is and this is 2's complement. A plus 2's complement of B nothing but A minus B. It means you are subtracting only, na? You doing addition but the result will become subtraction. Now you got the answer. When you got the answer, you will get in XS3. Now it is in XS3. To know that you do minus 3. What is the result? 5. If you add 2 plus 3, what should you get? 5. Alright, this is one example. Here you are not getting any carry, so you subtracted or you did A plus 2's complement of B. We'll do one more problem. Suppose I will add 5 plus 5. 5 XS3 8, 5 XS3 8. Now here you are getting carry. When you getting carry, you need to add 3. So it will become automatically 0 0 1 1. 3 adding to this, you will get the answer. Now this answer in XS3 you do minus. But here one logic you need to observe. 8 plus 8 you added, you got carry. When you got carry, I told add 3. Here also you need to add 3. Here also you need to add 3. That one you need to take and make it 4 bit, append 3 zeros at left side, add 3. Here also you adding 3. Here also you adding 3. Now you got result. Now 0 0 1 1, it is 3. It is in XS3. 3 minus 3, how much? 0. Now it is in XS3. This is 4. 4 minus 3, how much? 1. 1 0. Now 1 0 is the answer. Now how this will come? Now here this 0, this 4 will come here, you will do minus 3 0. This 4 will come here. How it is coming? This 1, it is taking here, see, 0 1 0 0. Now it is in XS3, you do minus 3, you will get 1. So this also has meaning here. But in previous case, what it will become? This is 0. This is 0. You no need to do anything here when you got 0. Okay. But when you got 1, you need to minus 3 to get the correct answer. So like this it is doing. To construct n bit XS3 adder, you need 2 4-bit ripple carry adders and 1 NOT gate. Now final, we'll finish in 5 minutes. Coming to the subtractor. However, half adder do 2-bit addition, subtractor will do 2-bit subtraction. However, full adder do 3-bit addition, full subtractor will do 3-bit subtraction. If you observe, half adder sum and half subtractor difference equation same. Half adder carry is AB, but half subtractor borrow is A bar B. A bar is coming. Okay, that is the difference you need to observe. And if you observe, sum of full adder and difference of full subtractor is same, XOR operation, but this equation will differ, and this equation you can write in different ways. It is important, observe. And now what is important here, this table, how to write these values you will confuse. I will show one example. Suppose 0 minus 1 minus 0. How to do? First you do subtraction, 0 minus 1. How much? 1 1. You subtract this third bit, 1 minus 0 1 1. Always this side will become 1, borrow. This will become borrow. You write it borrow. This will become difference. So like this you need to subtract, this you need to practice. Okay, otherwise it will become wrong. Now in half subtractor, 0 minus 1 1 1, you need to remember it as a rule. Some people tell 0 minus 1 you cannot subtract a large number from small, you take borrow, but there is nothing not to take borrow. In the problems you can apply that concept, but now here there is nothing to take borrow. You remember it like a rule, remaining all are normal. Okay, like this. Okay, and when we go to arithmetic operations like basics means number systems, arithmetic operations, complements, Boolean algebra, logic gates, simplification of expressions, and logic like codes, those all comes under basics. When I explaining basics as part of arithmetic operation, that time I will show addition of two numbers, subtraction of two numbers. Okay, then tomorrow we'll discuss about sequential circuits. Sequence circuits means latches, flip-flops, counters, registers, state machines. Huge syllabus. If you take counters only, there are lot of things in the counters. Okay, so tomorrow I will explain exclusively counters only. So many counters are there. Okay, that will take nearly 1 hour to explain counters. That many counters are there. Okay, so now revision completed with respect to combination circuits. Now I will show the slides. If anyone have any doubt, you can ask me. I will suggest everyone, make sure first you should be good in concept. See how many slides, how much concept there in combinational. If you good in this, that is enough for DV exam. Okay. In additionally, if you have patience and time, you can practice some examples. But primarily, essentially, you should be good in the concept. Now, if you did not understand any slide or any topic, or if you have any doubt, ask me. Suppose some real-time examples will be there. You may see in Google, LinkedIn, somewhere. Suppose if that problem related to multiplexer, before solving that, make sure you are good in concept of multiplexer. If you are good in concept, then you can solve that. If you don't know concept but trying to solve that example, that is meaningless. Okay, let me know anyone have any doubt on any topic.
Yes, sir.
Or any
Yes,
slide.
Sir, in parallel adder or repair carry adder, if you are in last carry, we need to neglect or we need to consider?
Last carry will neglect amma, because suppose if it is a 4 bit na, it can store only 4 sums, S0, S1, S2, S3. There is no space to save that last carry
Yes,
out.
sir.
Even it is 1 or 0, we will neglect.
Yes,
Suppose
sir. After we are adding 15 plus 15, that time we need to consider carry.
Suppose I will show 15 plus 15. Good. Here I will do.
1 1 1 1 and 1 1 1.
Okay, okay. I will show.
Without neglecting,
Yeah.
carry.
Suppose two numbers, number A 15, number B 15. I will show you. Generally, if we add 30, results should come. Suppose minimum how many bits we need to represent 30. For example, 30 if I take 15, 0. If I take 1, if I take 1, again if I take 1, 1. So 1, 1, 1, 0, 4 ones. Now this is 8, 4, 2, 16, 16, 8, 4 plus 2, 6, 2203. So if I want to add 15 plus 15, at least I need 5 bit. 5 bit triple carry adder. Okay. Now 5 bit triple carry adder means, now what will happen I will show. A4 to A0. Now you will take 1, 2, 3, 4, right. Here A0, B0. Here you will take A4. Now here S0 will come, S1 will come, S2 will come, S3 will come, S4 will come. C in you are giving here C0, C1, C2, here C3 going, and the C4 will be neglected. Even it is 1 or 0, there is no space, because 5 bit triple carry adder can save only S0 to S3. Generally when we add, suppose 15 means 1 1 1 1 1 1 1 1 1 1, sum 0 carry 1 1 1 1 1 1 1. Okay, suppose 1 1. Suppose now here generally if we take this one, then only it will become 30. But how many bits here? If you take 5th bit only, you will get correct answer. But if you taking only 4 bit, this will be neglected, so you won't get 30. Okay, Nama?
Yes, sir. Yes, sir.
Yeah. So any other doubts to any others? Okay, go through these all topics there in my channel. You can take lectures. If they are in private, you can ask Harshita.
ఈ వీడియో ఉంటుందా సార్ సేమ్ ఇది డివిజన్
Yeah,
ప్రీవియస్
yeah. This video also I will upload. That I won't keep in private. This exact video now only I will upload. And these all topics previously, each and every topic I explained. Those all also there in channel. These slides only very detailedly I explained each and every topic. Okay now. Okay, Nama, let me know still any doubts, any topic in combinational or any slide. See, 127 slides are there. Okay, suppose if no doubts at this time, later if you get any time you can ask me. Okay, so remember tomorrow counters, day after tomorrow registers and state missions, then another day latches and flip-flops. 3 days I will take for state sequential circuits, because that is so much syllabus. Okay, then I will explain basics. Then I will take mock interview on whole digital syllabus. Okay, okay, I am leaving.
Yes, sir. Thank you, sir.